You see the message, Jillian? Yeah. Okay. So basically, what happened was the teacher who said this question made a very major error in the value here, right? This value happens to include electrons in it. So it happens to include the binding energy of electrons in it, right? So this was the wrong value. Okay. So it turns out that so thorium has like 90 electrons, 90 electrons. So when you consider the binding energy of 90 electrons, okay, or rather, sorry, the mass. Sorry, when you consider the mass of 90 electrons, this value is off by quite a significant amount. Because 90 times electron mass in you, it's also gonna give you some significant value. And the whole question here was like completely wrong, right? Like because of this value, right? It doesn't make sense. I think the worst part of it, and I think I mentioned it in the video, so I recorded it. You can go ahead and show it to your friends, man. Right? I recorded it. Is I don't mind if you make a mistake. I don't mind if you just say that, okay, I'm sorry, I made a mistake. Okay, what I truly hated was after the during the CT review, they did not void this question, because if they voided it, they already voided like another question in the MCQ, and they did not void this question, and they said that, oh, the examiner just wanted it the way he said it, right? So this is the answer key. You just learn to live with it. So which was horrible, because there was an absolute error in this question, right? Let me just quickly go through a review. So I'm not gonna talk about like the details of the calculations, but I'm just gonna tell you this. All right. So it's all based on whatever I've taught you so far, right? So everything is based on whatever I've taught you so far. We have let's say for example, like A becomes B plus alpha, like this is the case, right? Uranium 234 decays into thorium by alpha decay. So basically this is what you see. And because it's a decay, you know that energy, right? Energy is released, right? You know that energy is released, right? Energy is released. Okay. Yeah, because by default all decays have energy release. So therefore, by default, we all also know that for sure the mass of A is definitely more than the mass of B plus alpha, right? That's for certain, right? That's confirmed, because we know that there's going to be a mass defect. In order for energy to happen, right, to be released, there must be a mass defect. So definitely the mass of A must be greater than the mass of B plus alpha. So if you check the mass, it actually makes sense, right? That's actually okay, because yeah, no, actually, I don't know. I can't remember the details, but there was something wrong with this number. Okay, there was something very wrong with this number, right? And then after that, you see that, yeah. So they asked the students to determine the binding energy per nucleon on thorium-230, right? Thorium, okay? So, so based on whatever I taught you guys so far in E3, E4, E5, okay? E3, E4, E5, if there's a mass defect and there's a release of energy, if there's a release of energy, how about the total binding energy? Like, how about the total BE? Like, what's the total BE on this side versus the total BE on the other side, right? Okay, okay. So I think if you refer to all the lessons, the total BE, right? The value, the numerical value. So don't care whether plus or minus, the numerical value. Okay, numerical value, right? When there's a release of energy, the numerical value must increase, right? So it must increase. Now, if that boggles your mind, then that means that you haven't been paying attention to all the lessons, right? Because it's a very clear-cut thing that I mentioned in the lessons in E3, E4, E5. You might have to go and search for it, right? I was doing a question on total BE. Like, you got to remember that if energy is released, mass defects, mass decreases, but the total BE, the numerical value increases, right? It increases. If you go ahead and search online, what happens to binding energy during a nuclear reaction when energy is released, right? You will see some textbook says it decreases. You will see some website says it increases. So it's like, who is right? Okay. Now, the reason behind that is because binding energy is supposed to be a negative value. So some of the textbook says that, oh, it becomes more negative, so that's a decrease, right? So and the websites are like, oh, let's not make it too difficult for people to understand, right? Let's just say that the binding energy increases, right? Okay, so right here, right now, I'm just telling you straight up that please just quote that the numerical value of the BE becomes larger, right? It becomes a bigger number. Don't care positive, don't care negative. If this is 2, this is 3. If this is 4, this is 8. If this is 9, this is 12. All right? So I hope you understand what does it mean to be a bigger numerical value. Okay? Right. So what happens is that the total BE will increase, right? Will increase, right? Increase, yes, with a release of energy. It increases with a release of energy, right? Okay. Unfortunately, right, if you try to do this question, you would realize that the binding energy based on the values given becomes less. And that was hella confusing for all the students last year, right? Because last year, like that previous batch, right? They followed instructions, right, to a T, right? So they were doing these questions and they realized, oh shit, something is very wrong. Okay, the binding energy, right? The value here actually became less, and then they were hella confused because they said, the first thing, right? The one of them came out of the exam said, Sam, I thought that decay release energy, so I thought the value is supposed to increase, right? What happened? Like, why did my calculations show that it decreased? Then they said that they didn't know how to do this, like they probably got it wrong. So ironically, they calculated it the way that the mark scheme wanted. So of course they got the mark. But the big problem, right? The big problem was that their concepts were completely messed up, right? So I told them, okay, you all sit down, let me just go through this, right? I recorded the video, right? Let's do a CT paper review, right? And you see the Instagram post, it was a video, like the actual YouTube clip also, I sent it out in the group chat as well, right? Like I just, like there was a hidden clip. I think I didn't show that one, right? I just let go. I was like, what the hell is the teacher doing? Like absolutely no professionalism at all. Because the teacher just simply said that, oh, the person who created the mark scheme wants it to be calculated like this, so we just follow, right? Like there is no concern about whether the students understood the concept or not. Like they don't give two hoots about them and the way they understand concepts. So which was horrible, right? So I had to do a lot of damage control. I had to do a lot of damage control because the students also went back to the parents and then they said like, I don't know what this Sam is teaching. Is he like, is he legit or not, right? Okay, great, right? So I had to go and do all the damage control. So you know what? For that, fine. I'll put up a post. I'll put it on Instagram. I'll put it on YouTube. You all go and see because I am very sure that I am 100% correct about this, right? No, yeah, this one here. I make mistakes also. I get it, but I absolutely hate it when that you make a mistake, right? And then you refuse to admit that you made a mistake, and you make the students feel that oh, you learned something wrong, which is the worst thing ever, right? So like whatever, right? I mean it's like whatever, whoever believes that their teachers are right and all that, also go ahead, right? I don't really care to, I don't really give two shits about like your results, right? But for you guys I do. Okay, Juliet, do you understand now? Yeah, right. There is something wrong with this question, right? So in fact, I think in Instagram post, I think I posted the correct value for thorium nucleus without the electrons, and if you use that value, you will be able to calculate it correctly. Yeah. Okay. Okay. Wait, hang on. Okay, hang on. Right. So it's gonna be a little bit messy. I guess it might be a bit messy. Let me Okay, let me do a bit of round robin. I think there's just a few of you at this point in time, so it's not overcrowded yet. I don't know where Celeste is. Celeste is she will be online, but then I don't know where she is. But anyway, so I'll do a bit of round robin first. Let me go through this question. Like, did anyone who sent this question? Sorry, anybody send me this question? Who was the one who sent me this question? I'm so sorry, I forgot. Oh, Celeste is here. Anybody send me this question? This one here, beam of electrons, then the de Broglie wavelength. That's you? Okay, sorry about that. Yeah. Okay. No, I really was at a mind stuck just now because I was so frustrated with my Grab driver just now. I was like, dude, what the hell? You got Google Maps, right? Like the Google Maps telling you to, yeah. And then throughout the entire ride, he was like, ah, ah, ah. I'm not like, okay, dude, right? Like, don't, right? Anyway, okay. So this is you. Are you okay with B though? Laura, Laura. No, I don't think I've gone through C before. Yeah, it's not. It's not. Yeah, so it's not. So anyway, for B, right? B, you should know this B, right? So I'm just trying to see whether you know how to do B because B would be a very likely question to come out. Either for tomorrow or for CTs or even for the IB, dude. Yeah. Like what's the equations that we have to go through? We have to run through. What's everything here? So like, what's the KE of the electrons? Yeah, what's the KE of the electrons, man? Nah, fine. No need to find. It's right here, right now. Electrons accelerated by 85 volts. I'm asking you what's the KE? Yeah, Q del V. Yeah, Q del V. Right. Right. Basically, this represents the change in EPE. Right. So you got two plates. Right. Two plates here like this. Right. The potential difference 85 volts. Right. One like possibly the forward plate is like positive 85. Okay, volts, and the electrons are being accelerated through the thing here like this. So the loss of EPE, the change in EPE is the KE, right? I'm going through this because I know D2 and D3 needs this, right? Okay, go. All right, so what's the value of it though? So the KE equals how much? How much is the KE? You guys didn't come down. I got snacks. So let's ask you to come and get snacks, Hey, Laura. Oh, they. No. Okay, wait, hang on. You're supposed to just say that the KE is 85 EV. First. Yes, okay. All right, so 85 EV, like straight up, you should always say this, right? SLHL, everyone, right? Straight up, 85 EV, right? And then after that, you're supposed to show the de Broglie wavelength. So de Broglie wavelength requires you to find momentum. So you got to find the momentum, right? So KE momentum, what's the link? Hey, for those the others who are online, right? Please don't just sit there and watch your friend burn. Come on. Uh-huh. No. Okay, square root of KE times 2m equals to P. So basically, you need to sub this into here, but you need to convert it in joules. You need to convert it to joules, right? Any physics equations other than from the one that has the Bohr's equation that has EV, everything else all SI units, right? E equals mc squared, all SI units, right? This lambda equation to P, right? K equals to P squared over 2m. That's all SI units, right? So joules, kg, and momentum, like kg meters per second. Yeah. So you can find this, right? Huh? Okay. So part C is not in syllabus. Okay. But let me show you what's happening. Okay. Part C, so circular aperture is not in syllabus. Okay. Circular aperture is not in syllabus. Hang on. I did say that. So I'm not going back on my word. I did say it. Okay. I'm not going back on my word. Hang on. So you have electrons, right? There's a beam of electrons going into a circular aperture, right? The question is this, right? Firstly, I think the first thing is this: without knowing, right? Without like kind of like knowing what it looks like, what do you think they are trying to get at here? Like Why would you send a beam of electrons into a hole? Like what kind of effect are you trying to get at? Laura? No, excellent. That's the exact thing I want to hear. Excellent. Okay. So you have a beam of electrons going through a hole. You're gonna get diffraction. So you're gonna get diffraction like that, like that, like that, like that. You get what I'm saying? Right? And you're gonna get a pattern on the screen. Okay? Let me show you the pattern. Let me tell you that it's not gonna be tested for circular hole. Okay? If it's a circular hole, the pattern looks like this. You will get concentric rings of bright and dark fringes. Bright, dark, bright, dark, bright, dark. But it's a circular pattern. Okay? So there's diffraction here, and there's a circular aperture diffraction pattern. You realize that I've never said that before in any of the C's. Right? C1, C2, C3, C4, C5. I've never mentioned about circular aperture before. Right? And in fact, the angle, right? The angle. So for this particular case, the angle is between the central maxima and the first minima, that angle, the theta, the sine theta is equal to 1.22 lambda over b. Right? This was the equation shown in the data booklet, right? Laura? No. So this is the equation shown in the answer key, right? Am I right? Yeah, there's a 1.22, right? I think someone else was asking me about the 1.22 as well. Just take note. This is not in syllabus anymore, right? Because you don't deal with circular aperture, okay? Right? But you sort of have to kind of like guess that, yo, it's diffraction and other kind of things, right? Okay, and then B will be like the size of the aperture, right? The diameter of the aperture, right? The hole, okay? Now, the question is this. Can they make this into something that is in your syllabus? Because I said that this is not in your syllabus, right? Can they make this thing into your syllabus? The answer is yes, absolutely yes. They can use a single slit. Okay? Right? They can make it into a single slit. And when they make it into a single slit, suddenly you need to know this whole thing. Okay? So I'm changing this now to a single slit. Right? Single slit like this. Right? So with a single slit, okay? Right? And this is the screen, right? What does the pattern look like for a screen? A single wave going into a single slit, right? And what kind of pattern do you get? You will get a wide central fringe, followed by the very small, insignificant bright fringes on the side. You will get a graph, a graphical intensity, right? A graphical intensity that looks like this, right? So like that, like this, like that. Whoop. Okay, and then you suddenly realize, oh my god, that's single slit. Yes, it is, because now we make the electrons behave like a wave, and therefore we are just showcasing single slit diffraction pattern. Okay, single slit diffraction pattern. And again, a recall of what was the important points on single slit. It was the center of the central maxima, as well as the first minima, right? First minima, right? And nothing else is important at all, right? For this single slit. Okay. So if they wanted you to do something to it, okay, right? Then you have to understand that what they want is the angle between the central maxima, right, and the first minima, right? That's the angle, and the angle is equals to lambda over b, where b is the slit width, right? I mean, technically it should be sine theta lah, right? Sine theta, but if the angle is small enough, you'll self-approximate lah, right? Okay, but there you go. Suddenly, this thing is definitely in your syllabus. You literally will have to know how this thing works. Okay, yeah. Oh boy, that's gonna be a doozy. All right, but it's not in the question. The question did kind of like show you that electrons with the same kinetic energy are incident on a circular aperture of diameter 1.1, right? I don't know what's the actual question itself, because I said I don't know what's going on. Like, you know, part C, where's the rest of the question? I don't see the rest of the question. But you did send something else, which was this. Is that right? Yeah, okay. So you did send this. It says, incident electron beam fired at aperture. Aperture, there's a detector there, there's a detector. The detector sweeps side to side like this. Let me copy and paste this onto my PowerPoint. You know what? Actually, I will paste it right beside here like this. So instead of a screen, you got a detector instead. Okay, right, there you go. So they got a detector, and the detector could detect, right, the intensity of the electrons, right, kind of like sweeping from here to here, kind of like this, right? The detector sweeping side to side like this is like the detector sweeping side to side like this, right? And basically it's telling you that, oh, the pattern, or rather the intensity, okay, the intensity of the electrons was like this. The intensity was like that. Okay, right? And then you might be like, what's that gonna help with anything, right? So if you look at it on the other side, okay, if you look at it on the other side, I mean, ignoring the fact that it's the aperture, let's say I just change this question to a single slit, right? Let's say I just change it to slit, right? The calculations, everything all the same. You just drop the 1.22 from the answer key, right? So you should, I don't know whether you realize this, but this pattern here is similar to this, and basically that's what they're trying to drive at, right? Right, what's the point of giving you this graph? The graph here wants you to find the angle from the central max to the first minimum. This is the first minimum. It's a minimum, it doesn't have to be zero. Minimum just means the lowest intensity, so that's a minimum. Okay, down here like this. And then I think the angle is 0.15 radians, or is it slightly a bit more? Laura? No, as in like you have the paper with you. Okay. I suspect it's slightly a bit more than 0.15. Let me just do a quick check on this. No. Okay, no, it looks pretty much perfectly on 0.15. So the working for this will be sine 0.15 radians is equals to lambda over b, right? Yeah. Or maybe you're supposed to find sine theta with lambda over b. Given the lambda that we found previously, right, the lambda that we found previously, and the b that they are asking for in the question, which is the 0.13 mm, okay, then you're supposed to find this theta there, and then say that, oh, it's similar or something like that, right? At the end of the day, they're asking you to do this. Use your answer in B to explain how data from the graph support the de Broglie hypothesis. So the first thing is you need to throw out what is the de Broglie hypothesis. So what is the de Broglie hypothesis, Laura? So basically, yeah, moving particles have a wave-like property. Yes, sorry, you were saying. Yeah. Okay. So basically, moving particles can behave like a wave, right? And what can a wave do? What do waves do? Wave can. What can waves do here? What can waves do there? No. I'm pointing to you the answer. Yeah. So waves can interfere, can superpose, right? There's principle of superposition, right? So yeah. So this electron beam is behaving like a wave, right? It's doing diffraction. It has similar angle to the graph given and all that. That's the point of this question, right? If anything, the only thing that changed was that I, instead of using the aperture, I changed it to a single slit. So again, this question is now relevant to you. Okay, right. Let me do a bit of a round robin. Let's go to Joel now. Celeste, do you send me anything? No, wait. Joel, you send me. Okay. What? Which one? This one? Okay, okay, that one I'll settle with you. Let me go to Luke. Sorry, I think Luke has sent me some stuff previously, and then I wasn't able to reply him because unfortunately you went to bump it, and then the message went up. Then I was like, eh, I thought you asked some questions, and I forgot about this. Okay, Luke, do we start with this? This one, I have to start with this one. So this one will be which chapter? Sorry, the one that I just showed. This one will be which chapter? What's that? This is D1, This is D1. Okay, right. Did I send the working for this in the group chat? I don't know whether I did. Okay. So basically you have two smaller metal spheres, and then later on you have two bigger metal spheres, right? And you correctly, unfortunately, what? Right. So oh, okay, okay. Oh, technically speaking, this is 2R, and actually this will be like 4R, right? Isn't it? I mean, it doesn't really matter, lah, right? The ratio is still the same. Yeah, hello? Yeah. So 2R and 4R, okay? Right. So one of the biggest things that students miss out on when doing this question is that the mass changes as well. So it's not the same mass as before. So it's still the same steel, the density is still the same, but the mass is now different. So if let's say this was M and M, right? I mean, we don't even have to put M1, M2, right? Because they're of the same mass. So it's kind of like M and M. What are the new masses now? Right? So if you double the radius, so I mean, each one is R, and then you double the radius, now it's 2R. So what's the new mass here? Anyone? What's the new mass? Hey, those online also, if you're here, right, you might as well just be like, be helping yourselves. What's the new mass here, guys? No? 8M. 8M and 8M. Do you know why? Do you know why? Okay. So it's still the same steel, but you increase the volume. These are solid steel spheres. These are not hollow. They're solid steel spheres. They're made of complete steel. So if you switch it out for a bigger steel ball, then you need to figure out how much more times the volume has increased. This is math. Volume of a sphere is 4/3 pi r cubed. 4/3 pi r cubed. So if you double the radius, you are cubing the double. So 2 cubed is 8. So the volume has increased by 8 times. So the mass of each sphere has increased by 8 times, or rather, the new sphere is 8 times the mass of the original sphere. So if I ask you, so if I tell you that, oh, this is the force, right? This is the amount of force originally, F equals to gm squared over 2r squared, okay? Then what is the new force here? Right, what is F2? Then F2 will be G 8m squared over 4r squared, and then you compare. Is that okay? You can do that now? Yeah? I'll leave that to you. Well, let me do one more for you because I think I really delayed his questions before. Okay, sorry, where do you get the next question from? This one? Is it from my practices? This is from my practices, is it? Huh? Where, sorry, from where? No, yeah, I know, but where is this from? Sorry, this is the exam style questions. Um, so that's a bit weird because if it's the exam style questions, Um, well, technically you can do this lah. Yeah, you can do this. So very quickly, okay. GMM over, well, it will be something like that, right? Okay, sorry, you drew a satellite there already. This is R, right? So R squared equals to mv squared over R. Okay. So if you rearrange it, basically you get GMM over R equals to mv squared, right? So if you were to increase the orbital radius, if the orbital radius increases, I mean the m cancels out anyway. So if we increase the orbital radius, then the velocity will decrease. Okay? I mean the mass obviously doesn't change, right? So it's either the speed increases or decreases. So the speed here will decrease. So A is the answer. Okay? Yeah, you should be able to do this. Do you understand this equation up here? That's Fg equals Fc, yeah? Okay, you mentioned about structured questions. Hold on, let me just look for the structured questions. Uh, like what? Is it the aluminum one? No, sorry. Huh? Aluminum. This one? Are you talking about this one? Okay. So the question is asking you whether is it possible for aluminum to spontaneously do alpha decay. So we have to kind of like see, right? Yeah. So if it does alpha decay, it will be what? 4 minus 2, so that's sodium. That's why they're showing you sodium, right? So will this aluminum decay into sodium with a alpha particle here like this? Okay. So I guess the question will be, what are the information given to you? Did they give you BE or did they give you mass? If they give you mass, then you obviously have to check the mass. So, and if they ask you spontaneously, it means that they're trying to suggest to you whether or not it decays. But we do know, I mean, hopefully from the start of the lesson, that if it was to decay, the mass must decrease. So you got to have to check the masses on both sides. Do you get a decrease in the mass? I'm not talking about mass number. 27, 23, 4, obviously mass number is conserved. We're talking about the specific mass. Okay? So what you have to do is to check 26.9815 U, and then you check 22.98. Or I think you did add up. Okay, there you go. Right. So 26.9815 and 26.9924. Right. So the answer is no. That's not gonna happen. Aluminum will not have an alpha decay. Right? I mean, it could do something else. I don't know. We don't really care about that. The question is asking you, would it be able to do this? The answer is no. Why? Because there's a mass increase. Right? There's a mass increase. A decay will not ever result in a higher mass. A decay will always result in a lower mass because you need to release energy. In fact, for this to happen, if you want this to happen, which for goodness knows why you want this to happen, but if it does happen, you will have to add in energy here, which means that it won't be spontaneous anymore, right? That's why they're trying to drop the hint here, spontaneous, right? They're trying to ask you whether there's a decay, right? But no, yeah, okay. So the answer is no, and you have to explain. So you have to compare this mass to this mass and say that there was no mass defect, no energy will be released, right? Aluminum will not spontaneously decay, undergo alpha decay. Yeah. Okay, there we go. Right. Your next question is a B3 question. Is that right? Your next structured question is a B3 question. Yeah. Okay. So I will have to reserve that for later. Maybe you and Celeste stay back after this. Right. Okay. Then for the rest of you, so all of these are what from past year CTs, is it? Okay. So what's the kind of like the question here? What's this? Second part. How do you do this? I I think in order for the second to understand the second part, you should be like very aware of why this is wrong. Like this is the crux of why you know, like your second part, you may use a wrong you might use a wrong value for it. Like this is the thing here. So the question is, do you know why, right? It's the cosine 56 included in this calculation here. I mean, you did do corrections, but the question is, you know, yeah, okay. So the reason why we have to split, right? Which I think I did see you split, okay, right? I think I did see you split. Uh, I'm sorry, who marked this? Someone marked it, is it? Oh, okay. Wait, hang on. Then where's the answer key from? This is wrong, yeah? It's not cosine, no? It's sine. Why would it be cosine? Magnetic field is directly vertically. Okay. Sorry. That would be my bad. Sorry, I didn't see that at first. So in this annoying example, okay, it's such an annoying example actually, right? The magnetic field is directed upwards like this. So it's a bit different from the way I draw in class, right? If you notice, I done the helical motion as well, right, in class. Okay, so but the magnetic field is like this. Okay, I totally missed it, right? The second sentence. Magnetic field directed along the y direction. Okay, and you have a particle that's going in at an angle like this, right? At an angle like that. So yes, you have to resolve it to the vertical and the horizontal, and if you resolve it, sorry, you will get this and this, right? And since this is at 56 degrees and this is I'll call this u, so I'll call this 1.5 times 10 to the power 6 cosine 56 degrees, and this is 1.5 times 10 to the power 6 sine 56 degrees. So this is like D2, D3, guys, right? This is for everyone, right? D2, D3. This is charged particle in a magnetic field, right? So yeah, magnetic field. So you kind of like have to realize that the vertical component of this proton has does nothing for the circular motion for this proton, right? This proton will experience a circular motion. If you use your left hand rule, right, force field current, okay, right, you would basically have field pointing up, current pointing to the right, okay, not diagonally, pointing to the right, because we resolved it already, right? So we take, and since this is a positively charged particle, right, left hand rule pointing to the right, and therefore this particle is going to experience a circular motion in this plane, right? It's going to experience a circular motion in this plane. So it's gonna like kind of like do this. So it would just like, like, yeah, like this. Oh, sorry, it will do this, right? It will do circular motion like that. Okay, and the circular motion is strictly due to this component of the velocity, 1.5 times 10 to the power 6 cosine 56, right? Like it's due to this. It's not due to that one, because that one does nothing. That one just pitches it forwards only. Okay, right? I mean, that's what helical motion is, right? Helical motion is circular motion with forward pitch. So you got your particle here and it goes around like that. Okay, so the circular motion is due to this speed, right? But then it also has a forward motion, so the particle will just do this, right, as it goes up. So it will like not spiral, sorry, helical motion as it goes, right, forwards like that. Okay, so in a way, yes, I always forget to draw this extra thing on the side, so that, the magnetic field is big enough, right, to encompass the whole thing here. So what you will see is a path that goes something like that. Right? That will be the helical motion, right? It will be a helical motion going upwards like this. Okay? So the forward component is this, but the circular component is this. So that's why when you try to sub in into mv squared over r, right, you literally had to use this, right, 1.5 times 10 to the power 6 times cosine 56 squared, right, this component inside here, because that's the component that gives you your circular motion, right? That's the component, right, that's causing this middle finger here to point to the right. Okay, and then the particle will experience a force pointing out of the page, right? So yeah, that's exactly that. Okay. But so the thing is this. Then they ask you, so what's the number of revolutions per second made by the proton? So to find this, you have to use this because this is your circular motion speed, right? So this is the speed v of circular motion. Okay, circular motion. So then you would have to understand that in order to find revolutions per second, what's that? That's frequency. You have to find frequency. So circular motion frequency, what's the link? Right? So you gotta have your v equals to r omega, v equals r omega. Well, this is the v anyway, right? So that's the v equals r omega. V equals to r 2 pi f. And then suddenly you realize, oh, that's where the frequency is. Okay? And then we can use that frequency, we can use that to find f. But that would also mean that you probably will have to find the radius, right? Because the missing thing here, you have v already, you need to find the radius, which is given in the previous part, the radius, and then you can find this frequency. Are we okay on this? Yeah, so the key point is to use that component. I don't know what you tried. I think you just went ahead to use that original speed, right? Without the resolved version. Yeah. I mean, what's the kind of plot twist questions that they can ask? They probably can ask you how far would it travel upwards per unit time? Then that will be this vertical velocity, right? That would be like the pitch value, right? They could ask like these kind of questions. They may ask you, where's the center of its circular motion, right? For this particle, where's the center of its circular motion? Okay, then the answer to that is the center of this guy's circular motion is like here, like in front of it. Like I'm putting my fingers in front of it, like here in front, right? Because when you do your left hand rule, right, and the force points out of the page, you see my thumb there. I'm trying to point it out of the page, pointing towards your cameras, guys. Okay, your screens, right? The center of the circle is here, right? It's in front of it. So the charged particle will do this, right? It will do a circular motion like that. So as it goes circular motion, it goes upwards, right? That's your helical motion. Okay. Yeah. Okay. So Luke's questions kind of like I will come back to it because I think got a couple more questions, but I think I need to do a bit of round robin. Let me um let me go to who's next, huh? How about Chaco, do you have any questions? No, you're here for the show? You're here to watch everyone burn? Okay, Laura, do you have any more? Okay, let me settle Celeste. Okay, because Celeste asked me a question, I answered her, but then she she's like, she still doesn't understand. I'm so sorry. I'm not doing a good job. No, 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 no. It's probably me. Yeah, hang on. Oh, the question is embedded downstairs. Hang on. Eesh, I need to make it smaller a bit. Okay. Sorry, what? Ken, when I come back to you, yeah? Ken? Yeah. Let me just settle this one first. I mean, I'm doing all this because I believe all this is like somehow. Actually, where are all these questions coming from? Celeste? Partial CTs. Okay. Laura, your one? SJI. Oh, that one's a workbook. Yeah, that was a workbook. Yeah. Oh, you're getting question from there. Oh, because you've done the others also. Okay. Okay, listen up. Celeste, come your turn to shine. Come. Okay, they're asking for all possible energy level transitions, initial and subsequent, that would occur. So the key phrase here is the initial and subsequent. That's like the thing that's like, oh, that's my trigger point. Initial and subsequent. Okay, fine. So the idea here is you have photons. So, dude, he's not using white light. He's shining, right, a specific wavelength of 12.1 eV photons, right? So the question is, would this even be absorbed? Will this be absorbed by the electron? The electrons at the ground state. Will this photon be absorbed? Even I'm asking you whether it will be absorbed lah. Your job is to check whether or not it can be absorbed lah. Can it be absorbed? Why can it be absorbed? You mean it can absorb anything ah? What do I mean? I'm asking you. Okay, let's say I give you a 13 not 13 how about this one? Let's say I give you a 11 eV photon. Will it be absorbed? Do you think that it can be absorbed? Wow. Oh, that means you're missing the whole concept of energy levels, right? Wait, let me just double check. Energy levels is E1, right? Is this E1? This is within your syllabus, right? Am I right? I mean, I also must make sure that you are doing the correct thing also lah, right? So Chaco, you can confirm that it's within syllabus, huh? Okay, so this energy spectral energy levels. Celeste, energy levels. What's the criteria for the photon to be absorbed by an electron with regards to the energy levels? Like there must be there. What is the criteria there? The energy of the photon must match exactly one of the transitions. Like the transitions, it must match exactly the transitions. If it doesn't match the transition, it will not be absorbed. The rest of the photons will just pass straight through. Do you remember that? That was in E1. That was a whole lesson on E1, right? So my question to you is, can you figure out whether this 12.1 can it be absorbed by the electron on the ground state? Can, but why? Why can it be absorbed? So you're saying that because the transition here, so you're telling me that due to the transition from here to here, and the transition is 12.1 eV, right? This allows this electron to absorb that photon into it. Is that what you're saying? How about if I use 12.2? Can or not? If I have another one, right? More energy, 12.2. Can it be absorbed? Yeah, absolutely not. No way. Because this electron, this photon will just pass straight through. Like it will not be absorbed. Well, 12.2 will not be absorbed, right? Because it doesn't match, right? The transition. You get what I'm saying? Yeah, so 12.2 cannot. I'm just trying to test your understanding because I don't know how much of this you know or you don't know. I mean, here's a bit confusing, right? I mean, traditionally what do we use to shine on this hydrogen gas in order for the electrons to excite? Like what do we use in the first place? What kind of light? White light. We used to use white light because white light contains all the photons, right? It contains all the photons, and then the electron will just only absorb some of them because there's only some specific, right, transitions that they can absorb, and therefore you know, when you shine white light, right, the electron can only absorb some of the specific photons. You get what I'm saying? Right? It won't absorb, it won't just absorb anything that it feels like it wants to absorb. Okay, it's got to be specific, right? Okay, so in this particular question, they are specifically only shining energy, photon energy of 12.1 eV. So it's not white light, it's monochromatic light. It is just a single photon. So the question is, can this photon be absorbed? Since there is a transition from bottom up, the answer is yes, it can be absorbed. So it will be absorbed to level 3. The electron, right, this electron at the bottom here will go up to level 3. Okay? All right, let me do a side question. Let me do a side question, guys. Everyone pay attention now because this is kind of important. All right, let me do a side question. Let me try this out now. See whether your understanding is rock solid or not. I have an electron here, okay? All right, but I give you a photon of, hang on, I'll give you a photon of, wait, 3.4 minus 1.5. I get 1.9. Okay, so how about this? I have a 1.9, right? 1.9 EV photon. I have a 1.9 EV photon. Okay? Right, 1.9. So you know what I'm trying to do here? I'm trying to entice you into saying yes because, you know, the transition here is 1.9. Okay? Right, I'm trying to entice you into saying yes. Okay? I use a single photon, right? Single wavelength light, sorry, not single photon, single energy photon, right, light, and I shine it on this gas, 1.9 eV, which happens to correspond to 2 and 3. So my question is, will this photon be absorbed? You see? I'm trying to entice you to say yes. I'm trying to coerce you into saying yes. Right? Photon 1.9 eV matches exactly this one, 1.9 eV, right? So will this photon be absorbed? The answer is no. It will just pass straight through. Okay? Then of course the question is, wait a minute, why? Didn't I just say that it has to match exactly? Since we have an exact match, why is this photon not being absorbed and it will just pass straight through? And the answer is, the electron is at the ground state. It hasn't gone up yet. So it hasn't gone up yet, it can't absorb. The only way for this electron to absorb this 1.9 is if this electron is at the top here, right? Then it can absorb. And that is why we use white light. Because when we use white light has all the photons. There's a chance that the electron can already jump up to the second level, and then you absorb the other photons that can enable it to jump up to the higher levels, right? So if your electron is at ground state and you use 1.9 eV, which matches this value here exactly, it will still not be absorbed because it's not there yet. So it will just pass straight through. This photon will not be absorbed. So you gotta have to make sense of, apart from like, you know, oh, it must match the transition, it must also make sense that whether or not it can absorb. Okay, so the answer is, for this question, right, 12.1 eV can be absorbed because it does help the electron to go from ground state to level 3, so your electron will be there. Okay, your electron will be up here. Do you understand this so far? I wouldn't bother going into such depth if I'm a hack job, right? There's a reason why I need to go through all this in depth. Celeste, are you still there? Okay. So they're asking you all possible atomic level transitions, initial and subsequent. We have just done the initial. This is the initial. So the question is, what's the subsequent? So you got to remember, once the electron is excited, what does it do? Yes, if you're at level 3, what are the possible pathways of you going down back to level 1? Level 2, level 1, or straight to level 1. That's right. So basically, right, you absorb one photon, but there is a chance of you to, right, emit 3 different photons, right? I mean, of which one of the photon was original one as the one that was absorbed, right? Okay, so that's why, no, then the answer for this one is that the answer is 3, right? The answer is 3. So So the upwards, right, the going up, the excitation going up is considered as 1, which is the same as 3 going back down to 1, right? So yeah, but if actually that's the thing, I will be very afraid. I will be very worried. If I'm sitting for your CT, right, and I see this question, I'll be like, these teachers, I don't know whether they're trying to be tricky or they just didn't realize. Is an upward transition the same as a downward transition? What if you say no, it's not the same? Okay, then I would literally write it all down. I will say that there's an upward transition from n equals to 1 to 3. There's a downward transition from 3 to 1, 3 to 2, 2 to 1. Okay? Try, I dare you to take away one of my marks. I will see you at the HOD's office if you dare to. Yeah. Challenge them like that. Huh. Yeah. Okay, okay. So that one I settled. Let's go to Joel. Okay, Joel. Okay. Whoa, what was that? Okay, so for Joel's question, this is a D1HL thing. So Chaco and Celeste, you can just like, block out for a while. And Luke as well, right? You can just block out for a while. Oh, lower part. Sorry. Uh, wait now. Okay. This is from where? Where is this from? It doesn't look like mine. Is it mine? Shit. What am I doing? Oh, where'd it go? Okay, sorry. I love PowerPoint, but sometimes it doesn't really love me. Yeah, wait. I need to do some cropping first. C part 2 ah. Huh? I don't know. Okay. So I don't know what answer key says. I don't know what answer key says. Right. In fact, I mean, usually I don't refer to answer key until like usually when we do practices, I would encourage students to try to recall what is in my notes or what I've gone through before we look at answer key. Because the IB answer key happens to be one of the worst answer keys in the yeah. Because they sometimes they show shortcuts and then like nobody understands what they're doing. So sometimes I just tell the students, I just follow my train of thought. You want total orbital energy? Is there an equation for that? TE of orbit? I mean, sure. But is there an equation for total energy of orbit? I don't think it's in a shared drive. I don't think it's in a data booklet, I mean, right? But if you remember anything to do with orbital energy, is that graph, right? Is that graph again? My gosh, what graph? Right? That three-line graph, this one, and this one graph, right? Yeah. Then kind of like when we went through this concept, you got to recall the equations, like oh, what's the equation of the KE? Right? The KE is half G mm over R. Right? What's the equation of the GPE? The GPE is negative G mm over R, right? Like this. And then also what's the total energy? Right? This one plus this one. So when that happens, it becomes negative half G mm over R. Like that's the equation for total energy. So if you ask me to find what's the change in the total energy, then what I'll do is I'll just find the change, right? Being negative half G mm over, well, I mean with final minus initial, right? So R plus 2 km. 2 km is 2000, right? 2000 meters, right? Minus half G mm over R. Something like that. Do you have the R? Yeah, you have, right? Yeah, you have the R. So I'll just work this out. I don't know what they're saying there. It don't sound too right to me. Either that or they're using the graph, or either that they're doing some other calculations for potential energy. I mean, I get that. I know what they're doing, right? But if let's say, if I were to advise anyone, like, how do you do this question? This is my advice, right? Like, yeah. They ask me for total energy. Okay, I'll go find total energy, right? I have all the values, right? Ah, shoot. So that's the problem. That's where we're stuck at, right? Okay, so that's where we have a problem then. Okay. So since they didn't give the mass of Earth, right? Then you probably will have to. Do you have the mass of the satellite? Yeah, you do. Then you probably have to recognize that the potential, right? V of Earth, right? So potential is negative Gm over R, right? So the potential at the radius is this, right? This one here. Then you have a value. You have like this value and this value, right? You can actually use that to find the mass of the Earth, right? And then later on find the other potential, which is negative Gm over R plus 2000. Yeah. Yeah. So you're right. Right. I didn't realize that, but yeah, they didn't give the mass of the Earth, so I would have been stuck as well. So you need to quickly understand that, oh, if they are not given mass, but this is the way to calculate total energy, then I have to find another way to find the mass, right? And then from this equation, since you gave me potential, give me R, right? I can figure out what the mass is. Yeah. Okay. Yeah. So that's for that one. The next one. Oh, that's it. That's it, huh? Okay, then back to Luke. Anybody else am I missing? Jillian, do I have any more questions with you? Okay, so you can send that to me. Let me just go through this very quickly. Again, this is HL for E2, right? E2 HL. Sorry, Laura, you're next before I go back to Luke. Okay. I know you said that you resolved it, but I just want you to learn how to do this. I mean, I just want everyone to, all the HLs to learn how to do this as well. So we have two identical negative charges of 5 microcoulombs and a positive charge of 5 microcoulombs placed along the circumference, and they ask you ask you to define this. And then what was the actual question? What was the actual question? They asked you to find? Eh? Oh, find electric potential in the middle. Okay, so find electric potential in the middle. Okay, so here's the thing. That's why I say the answer key. Sometimes you look at it, right? Like it doesn't really make sense. So let me explain what's going on here. What's electric potential again, Jillian? Yeah, I know that's the definition, but don't give me the definition. I'm not looking at the definition. What's your understanding of what electric potential is? Volts, right? Remember, it's volts. So a negative charge will give you what kind of volts? Negative volts, negative volts. Negative charge will give you what kind of volts? Negative volts. Positive charge will give you. So the idea here is, right, the voltage due to A at here, the voltage due to B at here, and the voltage due to C at here, right? You just sum up all their voltages. So V net is equal to VA plus VB plus VC. Now conveniently, B is negative, C is positive, so in a way, they cancel out. So it's not that V net is only due to A, right? It's more like mathematically when I add A to B to C, right? B and C have opposite voltage, same amount, they are the same distance. So you're only left with like VA. So sometimes the math scheme shows you VA, then you're like, oh, why do I ignore B and C? It's not that you ignore B and C, they cancel each other. Okay. If let's say you didn't have C, Dylan, just a quick side question. If you didn't have C, okay, what will be the V net in the middle? Yeah, and basically that would have been what? 2 times of VA, right? Yeah, it will be 2 times of VA. It will be like, oh, it's just double the negative. Okay, good. So There you go. That's for this one. Sorry, what's the other question you said that you wanted to check in with? Oh gosh, that sounds a bit vague. Uh, for what equation? For which one? Now point. Let's talk about now point. Is it? Okay. So let's say plus 5 microcoulombs. Are you talking about E2 or D2? E2, but E2 is photoelectric effect, right? Huh? D2 Okay, okay. So plus 5 microcoulombs minus 2 microcoulombs, right? Where's the null point? This is for everyone. Where's the null point? Null point is here, right? Why is it the null point? It's the null point because the E field strength from the 5 is pointing this way. This is the E field strength of the plus 5 microcoulomb. And the E field strength of the minus 2 is pointing that way. So E field strength of the minus 2 microcoulombs, right? And then sometimes we are asked to find what? We're asked to find the distance, right? Like we have to find, oh, what's the distance between here and here? Like, this distance here. Am I right? Yeah? Hello? Yeah, if let's say this is like x, for example, right, x and d, for example, then like how does the equations look like, right? Okay, so the equations will be something like this. Then you have to write out, oh, kq over r squared equals to kq, right? Kq, whoops, over r squared, right? Like the E field of the minus 2 is equals to the E field of the plus 5. So your K, then I say put a 2 here, then R squared is D squared, and then K, then a 5 here, right? Then I put X plus D squared. Is that your question? Why I don't put a negative sign there? Yeah? Right? So the idea here is if you do put a negative sign, you'll be in trouble. Right? Because if you try to square root it, you'll be square rooting a negative number. Then So how is it that you can leave out the negative sign? I think for a lot of the equations that I do, I like to think of it as the magnitude, right? The magnitude of it. So the magnitude of the strength, right? How strong the field is, right? The strength is equal. So I just write down the magnitude of this is equal to the magnitude of that, right? Then I don't have to go and deal with the negative sign. I don't have to bother with it. Okay, but I get it because some teachers are always teaching, right? When they're teaching, right? Oh, you all must pay attention to the negative sign. The negative sign is there, right? The kind of thing, right? So it gets very, very unnerving. So I'll tell you this, okay? So what is the by right thing to do? What is the correct thing to do, right, Jillian? The correct thing to do is to write something like that. The negative of the negative 2 microcoulomb is equals to the positive E field strength of the 5 microcoulomb. It's supposed to look like this, right? So in a way, right, when there's a negative sign outside and then there's a negative sign inside, they just kind of like they cancel each other out, and therefore I always don't bother drawing it. Like I don't write down the negative signs. Okay? Yeah. But yeah, it's a bit of like sometimes it's more like I just pay attention to the magnitude of it. Okay, I'm not too concerned about the negative sign because I know your math is like oh, it's very important to put the negative signs in the correct positions and all that. But do you know why I put a negative sign here? That's right, opposite direction. So if I were to flip this one over to this side, then the both of them will have the same value. So to me, I know I actually am at fault for this. I'm sorry about that. But I just kind of like just put down the magnitude and the magnitude and like do this. Yeah, you get. I understand what you're saying because I'm very aware that I really usually do not like to put the negative signs because it's just hella confusing to students. So I just say, oh, this one the value of this is equal to the value of that. right? It's like binding energy. It's like, oh, the value of that is equals to the value of it, right? So the value itself, the number itself. Yeah. Okay. That's a lot of it's very hard for me to point out when I think the other scenario the other scenario is this. The other scenario was what's the like let's say midpoint here. Let's say midpoint here. What's the E field strength there? Like at the midpoint. Okay? Right? So the E field strength will be something like this. So the E field strength from the plus five, right? The E field strength from the plus five is what? It's pointing to the right. And the E field strength from the minus two is pointing to the right as well. Okay? So what is the E net? All right, at the midpoint. So the E net will be here. E net will be right the E of the 5 microcoulombs plus the E of the negative 2 microcoulombs, right? Correct or not? Yeah. Then when you add it up, when you try to do it, so it will be K 5 times 10 to the power minus 6 over. So I didn't put the micro on these two sides because they cancelled off, right? But for now I have to put back the micro. So 5 times 10 to the power of 6. Minus 6, right? Micro, 5 times 10 to the power minus 6 over x over 2 squared. Okay, then plus k, then 2 times 10 to the power minus 6 over x over 2 squared, right? This was the other scenario where if you go and put the negative sign, you confirm wrong one. So you take out when you have made sense of it. So you see the key thing is to make sense of it. If you don't make sense of it, right, you end up you literally will just end up like just doing it because the equation says so, right? So I'm trying to show you how to make sense of it. So the idea here is the E field strength of the 5 points to the right. The E field strength of the 2 also points to the right. So in a way, like I have to sum up, right? It should be a stronger field. If I put a minus here, then basically this term minus that term, I will get a weaker value, which is wrong. Yeah, so unfortunately, at the end of the day is making sense of it, right? Like have a have a very strong idea of should you be leaving the minus sign in or not. Like that's like if you can, I mean, not to say it's me, but if you can go through a calculation and you can point out that if you put a negative sign, how would it affect the calculation and why would it be bad and all that, that really really is a good indication that you're very good at this thing already. So you have to get there. So for every calculation that you do, you gotta ask yourself, should I put a negative sign in or not? And if not, why not? If I do, why I do, right? That kind of thing. Don't just be in a hurry to like calculate and bang out the thing so that you can get an answer, right? If students put a negative sign here, right? This one here, okay, the whole thing will be wrong. I'll tell you this, okay? If I'm a school teacher, right, I will set this very question every other year. Confirm because some bugger will forget one and then just put a minus sign there because they just see, oh, equation mark kq over r squared, kq over r squared, the q here is 5, the q here is negative, right? 2, then I just put it in now. How come my answer wrong? Right? Yeah, that's the reason why, because they don't have a good grasp of what's happening, right? So yes, it's not possible for me to go through every single scenario, but you just have to be very aware of it. Okay? Okay. Laura, I see your question now. Right? Oh, now the questions are all coming in, huh? Wait, after this I have to do loops one, huh? Wait, what's this? What's this? Did I understand this? Uh, did I not send this out before? No, as in like did I send this out before? I think I may have. Anyway, but for those who are not aware, this is E2, this is only HL, right? So this is photoelectric effect, right? There is something severely wrong with this question. What's the severely wrong with this question here? What's the severely wrong part about this question? You don't know, okay. So it's an IV graph, right? Okay. Even if you use a straight line, but by right it's supposed to be a curved line, right? Remember, it's supposed to be a curved line, like looks like this. Ah, then that means you and the teacher has also done the same thing. We all mistook this graph. So this one is obviously the teacher thought he was like, kind of like being smart about it, but okay, so this, I think the teacher took it from the wrong graph. Okay. Um, do you recognize this graph instead? You recognize this graph, right? Okay. I mean, what happens if I give you another metal, right? It has to be parallel. So I suspect the whoever said this question thought that the graphs were the same and probably thought that, oh, I can test the students about these two parallel lines. I'll put these two parallel lines here like this, right? And then give them a third line and ask them about it. But yeah, so the thing is that this graph, right, the gradient can never change because the gradient of this graph is h, right, Planck's constant, which is supposed to be a constant, so no other graph will ever have another gradient. Correct? Okay, so that's that. Anyway, this is the wrong graph, right? This is not the graph they're talking about. They're talking about the IV graph. So I go back to the IV graph, sorry. Right. How should the IV graph look like? The original one look like, Laura? It should look like the curve that I showed you just now. Like this. IV graph. It should look like this. I mean, I'm just telling you that the graph there is not quite right. But your teachers will just tell you that. Your teachers will tell you that, oh, the examiner wants it to look like that. You just accept it, right? Yeah, that's what they'll tell you. So it feels there's a very off-brand feel about it. Oh, but not your teachers, guys. Actually, not your rotational teachers. It's the other batch of teachers that caused the problem. Remember, I said the 2024 CT had a problem, right? Because of that rotational teachers. It's actually not your current rotational teachers. So there's a very high chance that you won't get erroneous papers. But that particular rotational teachers, that one I always get every other 2 years. Yeah. So your juniors, right? Phew, wow, I tell you, they're suffering, man. I tell you. Anyway, okay, no, this is the graph, right? Isn't it? What do you mean why? We've drawn this, right? Like, didn't we draw a version of this? Like, wasn't there like something like that as well? Then wasn't there there's one that looks like this and then kind of like one that looks like that? Like they cross over the sort of thing. Right? Oh, yeah, I mean, okay, I mean, let's try to understand why it looks like this first, right? Let's try to understand why it looks like this first. So what is this? Oh, by the way, again, now for the SL, just be careful. This is E2, this is only HL only, right? Just in case you're staring at this and trying to figure out what's going on. There's nothing. What? VAT. Intensity. Nah, bro, it should be. Oh, what the hell? Where's the original question? That's the question itself. Like, is there like a header? Huh? Yeah, it's current. So it's not intensity lah. It's current, right? It's current. But again, my point is that this thing is wrong. This thing is still wrong. Yeah, but why? Like, what's this thing here? Yeah, that's the stopping potential. What is it based on? Like the stopping potential is based on the light that you're using, right? Like the higher the stopping potential, the higher the frequency, right? Okay. Then what is this thing called? What are these flat lines called? No, these are called sets. Why stop thinking it's intensity? This is current. Current. Yeah. So what's this? What's this? What's these two things? These two things are saturation currents. Saturation current. Right? Rate. No. Yeah, I mean saturation current is basically the rate of the photons emitting electrons is at its maximum. So even if you increase the voltage any more positive, right, the amount of electrons being emitted by the emitter plate will reach a maximum. Like it wouldn't increase anymore because there's a limit to the intensity of the light, right? The light that you're using, right? The light that you're using. So when you shine a light, right, is the rate of photons like sort of constant? Yeah, it's sort of constant, right? I mean, if you want more, you can increase, right? You make it a stronger light. But otherwise, if you have a certain intensity of light, the rate of photon should be quite constant, right? Okay. So when it hits the metal plate and then the electrons jump out, the electrons start flying over to the collector plate, correct? It starts flying over to the collector plate. At some point, the rate of electrons is also maximum, right? Maxed out. Okay. Right? Especially if this plate is like made positive. Let's say it's a positive volts plate. Like you are attracting the electrons, it's flying over, it hits the plate, right? But the amount of electrons that can hit this plate is now limited, or the limiting factor is the rate of photons that's hitting this plate. Correct? Which is why there's this idea of saturation current, because the current is in the wire behind this plate, right? That's the current there, right? It's registered by the galvanometer there, right? So like no matter how positive you make this plate onwards like this, you should not see an increase in current after that, because you already maxed out the rate of electrons flying over, and the rate of electrons flying over is due to the rate of photons. Like no, like having a more positive plate doesn't make more photons coming down, right? Like if let's say you're using a certain rate of photons, correct? So by right, so technically speaking, if they had drawn this as a straight line, I think one of the key mistakes that the teachers made was they should have drawn it like that. At least they should have drawn it like this. You get anything? Yeah. So they should draw a flat line after, right? Draw a flat line after. If you draw in indefinite lines like this, X, Y, and Z going up like that, you know what that means? That means like your light, right, as you're shining it, right, you're increasing the intensity as you go along. It's like you're changing this to positive voltage and they're also increasing the intensity at the same time. Like you're giving more rate of photons at the same time, which is why the current keeps on increasing like that, which makes no sense. You're supposed to reach a saturation current, right? Yeah. So basically, what I mean, okay, notwithstanding that the graph is wrong, but okay, now we can start to talk about it. So the blue graph has a higher stopping voltage because it's more negative. It's harder to stop the electrons emitted by this light. Therefore, we can say that X has a higher frequency. X has the highest frequency. So X and Y have the same frequency. That's wrong. Okay, right. Y and Z have the same frequency because they have the same stopping voltage, right? Y and Z have the same, yeah, okay, right, that's right. And then Y and Z has different intensity. So the idea here is if they had drawn this saturation current, you realize that Y has a bigger saturation current than Z, which means that Y has a bigger intensity. So in quantum, you got to remember in quantum intensity is what? Intensity. What's the equation for intensity in quantum? I mean, I sort of don't see you write it. This happens to be wrong, by the way. Yeah, that's wrong. That's not intensity. I mean, if you had written proportional, I understand, but you wrote equal, that's why it's wrong. So intensity is, and some more small n, that's wrong also. Come on, man. Right? So intensity is NHF over T over area. What? What kind of nonsense? I just write out the whole thing lah. Aiyo. Okay, big NHF over T times divided by area. Okay, that's okay. I guess that's why that's a bit annoying. The reason why I would like to use big N is because I want to remind you that big N stands for big number, It is a big number. It's like 10 to the power 15, 10 to the power 20, that sort of thing. It's a big number, right? So specifically, you can even say that Y has a higher intensity than Z, even though they have the same frequency, they have the same F, right? The rate of photons of Y, N over T of Y is bigger than that of Z. Okay, so 2 and 3 only. Okay, let me go back to yeah, what? Stop, 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 stop. Gravitational fields and so you're talking about G, E, and B, is it? Okay, and then what's your question? Huh? What? Wait, what kind of? Uh-huh. I'm a bit lost as well. Cause, cause firstly, there's no potential energy in B fields. There's only potential energy in G and E fields. And secondly, if you're referring to the specific equation, so like what is GPE in the equation? So it's negative GMM over R, and then for EPE specifically, it is negative KQQ over R, right? Like these are the equations. So are you asking me when do we use these equations versus when do we use the work done equation? Yeah, I mean, what did I mention about when you use this equation? What does this equation give you? This equation gives you the spot value, right? It gives you the value at that point only. It doesn't help you find the change. I mean, the idea here is that if you have to find a change in GPE like this, if let's say you're trying to find a change in GPE, change in GPE is exactly the same as work done, right? If you do work to an object, it will change its GPE, right? If you bring it up, it will increase GPE. If you bring it down, it will lose GPE. So GPE is work done. Change in GPE is work done. But if you're looking at the potential energy equation itself only, that's only one spot value, right? So if let's say you want to use this kind of like equation like that, okay? So I believe I'm thinking you're talking about the work done. This will be what, M del V, is it? Yeah, M del V. Right. What is the change in GPE then? Change in GPE is change in GPE will be what? GPE final minus GPE initial. Is that right? I mean, I'm literally telling you it's the same thing. I don't know whether you realize it, but it'll be like what? Negative GMM over R final minus minus GMM over R initial. Do you see that? Do you see this? Do you understand what's going on here? Yeah, final minus initial, right? Okay, good. Can you factorize the M out? Yeah, what happens if you factorize the M out? Then you get M, right, which is multiplied by negative GM over R final minus minus GM over R initial. Do you realize what I've just done? Yeah, this is exactly the same as M V final minus V initial, right? Which is basically this. So if you're wondering why is del GP the exact same thing as work done, right? This is the reason why, right? But if you're asking me, so when do you use this equation? This equation is kind of quite useless on its own because this equation only helps you to find the potential at that very point. Like it doesn't help you to find the change in GPE. Yeah. But again, don't go into the spiral of like just sitting there trying to imagine things of like, when will they ask me this, when will they ask me that, when will they ask me this or ask me that. Like, get out of the spiral, just do the practices. Yeah, right. There's no such thing as like you sitting there and then trying to work out all the possible scenarios in your head. Then suddenly you'll do better in the tomorrow's test. No, it's all about grinding, right? So you got to grind the papers out. Yes. Okay. Sorry. Let me get back to Luke because I do owe him quite a few questions. So hang on. Let me just look at this one here. So again, the ideal gas one, I'll do it later. This one here. Oh, well, I mean, this one is again ideal gas, right? This thing here. Yeah, this is V3. But the thing is this, did I not send this out? I think I did though. I think I did. So I think I did something about the what is it again? The mercury, is it? Did I show mercury? Okay. Right, I will send this out for, oh man, I think I better target the SLs only, so because otherwise everyone's gonna be confused. So Celeste, Jaco, Luke, who else? Keegan, Gabriel, Kaylin, anyone else? I think that's it, right, for the SLs. Did I miss anyone? I'm so sorry if I missed anyone. Yeah. Okay, anyway, I sent it to you. So in that video, you will be able to understand the concept that's happening here. All right, calculations wise, I will deal with you in a while. So let me just wrap up all the more common topics for everyone. So I think your last two pictures were on B3 as well as that the other question on open flask one. So I'll deal with that with you later. So I think the last one will be the last few things that was relevant for everyone will be this. Sorry, Jillian, did you say that you have another question? Okay. So yeah, sure, no problem. Or you want to stick around and listen to this binary star question also can. Okay, cool. See ya. Okay, bye. Okay, look, for this one here, all right, this is a binary star question. So, kind of like the I think the working here kind of like shows kind of like maybe kind of tells me that you're not too sure what's happening here. So this is a binary star. Binary star is an even higher application of circular motion and gravitation, right? So you know what? I think the best thing is for me to send you the video on this. So binary star. Okay, hang on. Let me just send it out. Okay, so I did a revision on binary star there. And it's at 10 minutes only. It's 10 minutes. Yeah. So I mean, I can show you the calculation now, but if I show you the calculation, that's me like going through the whole thing. So I rather not. I'll leave the video to you. If you're still not sure about this, you just drop me a message. Like later tonight, I'll go through again. So later tonight, there will be another session for the consult. So if you are doing more questions, if you guys are doing more questions, I'll answer you. Okay, so I'll leave this to the video. One more question from you before I dismiss the HLs. Oh, wow. Okay, this is an annoying question. What's this again? Two spherical bodies in the diagram have the same radius. The sphere on the left has twice the mass on the sphere on the right. So, yeah, so 2m and m, right? So A, B, C, D. At which point does the net gravitational field strength of the two masses have the greatest magnitude? Okay, so the answer is A, right? This one is straightforwardly A. Okay, right. Oh, sorry. What's Dora the Explorer doing there? Sorry. Luke, are you there still? Okay. So A, right? So the question is like what they're asking for. They're asking for net G field, right? So if I have two spheres, right, then the G field is due to what? The G field is due to those two spheres, right? So at point A, there will be a G field due to the 2M. There will also be a G field due to the M as well, right? So if let's say I zoom in a bit, let's say this is A, okay, let's say this is A, right? Sorry, this point here is A, right? This is a 2M mass, and this is kind of like the M mass here like this. So there is a G field strength due to the 2M. Okay, this is the G field strength of the 2M, right? And then there will be a little bit G field strength by the M. Okay, right? Now it's a little bit because it's actually quite far away from the M. So one of the key things is I think that confuses students is, how come G fields and E fields, right, can pass through another body on? How come this mass here, right, can attract a point that's on this side, right, pointing this way? And the answer is yes, yeah. I mean, G fields cannot be blocked, right? E fields cannot be blocked also in a sense, right? So this mass can attract this point right through the body. So the total G field, right, for this for this mass, right, I mean from 2M is this arrow here, and then from this one is here. But we can explore the other points. Let's look at the other points. Okay, so let's say we try B, for example, B. Okay, now if it's point B, then the G field by the 2M, right, the G field by the 2M will be the same as that of A lah, right? So this one and this one here will be the same, right? Just that this one is pointing in. But from from M, the G field acting on B will be pointing that way. So it's kind of like, and somehow it will be a little bit longer as well because now it's closer, right? The G field of M at point B, right? So it's a little bit longer. So like this will cause it to be less because they're not pointing in the same direction. Same thing for this point. And then for the last point there, how about the last point here? Right, D. I mean, you know what? I'll just go through everything lah. Huh? So C also. So point C here like this. So point C, you will experience a kind of like a significant G field strength from M, and then you'll get a smaller, right, G field strength from 2M, right? Because now C is like further away, right? That's like C here, right? So C is like further away, so like that. And then for the last one, point D, you might be thinking, hey, isn't it both of them pointing in the same direction again, right? Yes, it is. So, right, this will be GM, okay? And this is G2M, right? But 2M is much further away from D, so, kind of like, yeah. Yeah, so in a way, if you compare A and D, A will definitely be bigger because the net field strength from 2 is much stronger. It's just that there's the additional, that small little GM there like that. So, yeah. Okay? You get it now? Yeah? Okay, for the HLs, if you want to, I don't think you should stick around. I think you should go and do more. So Chaco, Luke, and Celeste just stay on for a little bit more. I got only about 10 more minutes left, right, for my next class. So let me try to finish Luke's question on B3. Is that okay? Right, Joe and Laura, you okay there? Okay, bye-bye. Bye-bye. Okay, all right, so for this one here. So what's the question here? Open flask has this mass, ideal gas, 17 degrees Celsius. You converted to the Kelvins, very good, right? Then they ask you, okay, at constant pressure, okay, constant pressure. So you have a flask, okay, you have a flask, and you raised it from 17 degrees Celsius to 100 degrees Celsius. But the very strange thing, guys, the very strange thing about this is that the pressure is constant. Huh? Like, how is that possible? How is it possible that you increase the temperature, but the pressure is constant? Wouldn't the thing explode or something? Right? So unfortunately for based on no, IB wouldn't do this, right? IB will give you some clues. So unfortunately the school here was trying to like pull a fast one on the students. So what happens is that this flask is an open flask. Yeah, it's an open flask, right? Yeah, I mean it's written there, right? It's an open flask. So they're trying to be funny here. An open flask means that if you were to heat the gas will escape. The gas will escape. So as the gas escapes, the pressure inside is constant. Okay, so there you go. That's pretty much the idea here. So what happens is that means you got a initial state, you got a final state. So you got initial state, and then you got a final state, and your job is to find out the difference in the mass between the initial and final state. So it's basically PV equals to nRT for the final, right? Then for the initial, right, PV equals to nRT for the final, right? And then your job is to find the difference in the mass of the mass, okay? Mass of the gas, sorry. Yeah, I don't know whether you can find the number of moles, so we're just gonna assume that the N is in kg, right? Which is wrong, but I guess that's the only way we can do this, okay? Um, so what will happen here though? The volume is also constant. The volume is also constant. So PV is constant, right? P times V is constant. So if let's say you take the final minus the initial, like the two terms on the left hand side, they basically become zero. So zero. So you have nRT final minus n RT initial, something like that. Yeah. Did they give you the molar mass of the gas from the first part? It's just like that. There's no other information on what kind of gas is it or anything like that. Okay. Right. No, because it's a bit unnerving not to have the number of moles. So sure. I mean, what else? So essentially, you have like um. I mean, you can get rid of R lah. R is just constant on both sides, right? So if you divide by R throughout, the R disappears, right? So oh, I might like so basically the N initial T initial equals to the N final T final, right? So the N initial is here, the T initial is here, the T final is here. Your job is to find N final in terms of mass, and then you find the difference of NF minus NI. Okay, good. All right, so there you go. So that's sorry, what? Sorry, what? I mean, I'm not comfortable with that. I'm seriously not comfortable with that, right? N is supposed to represent number of moles, right? But for the like when you do ratio, right? When you end up with a ratio kind of thing, NITI, NFTF, right? The mass and the ratio of the number of moles is the same. Yeah, right. So the ratio of the mass and ratio of the moles is the same. So you end up just being able to use this equation to find the total mass, and then you use the final mass minus away the initial mass, you get the difference in mass. Yeah. Oh, and then the very last one? Yeah. I tell you what, the very last one, this one here, I think you should go and watch the video first. Yeah, to understand what's going on. Because otherwise you like, it'll take me a while and my next class is coming in and I'll be rushing through it. Um, but essentially once you watch the video, the idea here is that you see this gas that's trapped inside, right? Okay. So when you have a trapped gas inside, the PV is always the same. So P1V1 equals to P2V2. So like if you have P1V1 here, and then you look at the next scenario, right? The gas is now like kind of like expanded. So this is P2V2. Like the value of P1V1 is equal to P2V2. Like, yeah. Yeah. So the volume of the gas can be calculated based on the length of the gas column because the cross-sectional area is the same for both sides. So cross-sectional area times the length will give you the volume, right? Yeah. Okay. Celeste and Chaco, don't forget to do B3. I mean, I sent out all the videos for D and E, but then your test has B3 also. Yeah. Yes. I I don't quite understand what you mean by do you need to explain it or not? Yeah, but I think it's more like a touch and go. Like it's kind of like a like oh, what does a Geiger Mueller tube actually measure? It measures the ions. Where are the ions coming from? The ions are coming from ionized gases, right? The gas hits the thing and then it ionizes gases. So that's how we know what the count is, lor. No, no. Okay. Okay. All right. You see, right? I actually did go through that in class. So, it's not kind of fair to me and you yourself, right? So you basically have a clicker here, okay, and a battery here. So this is the high voltage that we're talking about, right? Okay, so inside this Geiger tube, it's basically a cylinder. It's a cylinder, right? It's a cylinder. It's a hollow cylinder with a gas inside. There's a gas inside. What gas? Don't care, right? So let's say there's a beta particle and the beta particle flies in, for example. Do you see the beta particle flying in? And then it hits one of the gas molecules and then it becomes a gas ion. So once it hits, it becomes a gas, right? Plus ion, right? This is a plus gas ion and a negative gas ion, like this. I don't know what like which ion becomes what, but essentially, if you look at it, the central electrode is all positive, right? The central electrode is all positive, 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 positive. The outside electrode, the outer casing is negative, so not negative, 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 right? So the question is, once the gas ion is formed from the decay particle colliding into it, like where does the negative gas ion go? It will go to the positive ion. Where does the positive gas ion go? It will go to the negative electrode, right? Sorry, negative gas ion will go to the positive electrode, right? And then positive gas ion will go to the negative electrode. So once they touch the electrodes, right, current will flow. So once the current flows, the clicker will click. So it will make a count, right? So this is where the count happens. Yeah, I went through this already. Come on. Yeah. Okay, good. No, yeah, no. So the thing is this: if I've gone through this before and you have the videos, right? You're supposed to use that, right? Because a very good use of my time will be for me to go through questions that you have, right? So continue to do practices. So for you, right, Celeste, I discover that you do have knowledge gaps, but actually whatever you're doing is the correct way of doing it. You have to find your knowledge gaps by doing the practices. And once you do the practices and you realize that, oh, this is something that I don't know, you have to admit that you have a knowledge gap and you have to go and catch up using the videos. Yeah, because these are all the things I've done before. Unless it's something new, like if you send me a question and I realize, oh, this is not something that I've done before, then yeah, okay, that's fine, right? I will then like go through it, willingly. Uh, okay, I'm done. All right, I have to go. My next class is coming in. See you guys. Bye, 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 bye.